order to learn more about this subject, we must do the wave packets. So this is the place where you really connect this neat solution of Schrödinger's equation, the energy eigenstates, to a physical problem. So we'll do our wave packets. Okay, so we've been doing wave packets for a while, so I think it's not going to be that difficult. We've also been talking about stationary phase, and you've practiced that, so you have the math ready. We should not have a great difficulty. So let's do wave packets. Wave packets with, I'm going to use A equals 1 in the solution. Now I've erased every solution, and we'll work with E greater than V naught to begin with. The reason I want to work with E greater than V naught is because there's a transmitted wave. So that's kind of nice. So how am I going to do that? OK, I'm going to write it this following way. So here is a solution with A equals to 1. E to the I kx plus k minus k bar over k plus k bar e to the minus I kx. And this was for x less than 0. And indeed, when there was an A, there was a B. If A is equal to 1, remember we solved for the ratio of B to A, and it was this number, so I've put it there. I'm just writing it a little differently, but this is, you know, a solution. And for x greater than 0, this is the solution is C, which was 2k over k plus k bar, e to the I k bar x. OK. Now we have to superpose things. But I will do it very slowly. First, is this a solution of the full Schrödinger equation? No. Is the solution of a time-independent Schrödinger equation. What do I need to make it a solution of the full Schrödinger equation? I need e to the minus I et over h. And I need it here as well. And this, you know, is a psi now of x and t. There's two options for x less than 0 and x less than 0, and those are solutions. So far, so good. Now I'm going to multiply each solution. So this is a solution of the full Schrödinger equation, not just the time-independent one, all of it. It has two expressions because there's a little discontinuity in the middle, but as a whole, it's a solution. That is the solution. You know, some mathematicians would put a theta function here, theta of minus x, and add this with a theta of x, so that this one exists for less than x, x less than 0, and this one exists for less greater than 0. I will not do that. I will write cases, but the philosophy is the same. So let's multiply by a number, f of k. F of k. Still a solution. K is fixed, so this is just a number. Now, superposition. That will still be a solution if I do the same superposition in the two formulas. Integral dk and integral dk. That's still a solution of the Schrödinger equation. Now I want to ask you what limits I should use for that integral. and if anybody has an opinion on that. It might naively be minus infinity to infinity, and that might be good, but maybe it's not so good. Okay, it's not so good. Why is not so good, minus infinity to infinity? Would I have to do from minus infinity to, am I forced? Does anybody force me? No, you're superimposing solutions for different values of k. You're superimposing, you had a solution, then another solution for another k, another solution. What goes wrong if I go from minus infinity to infinity? Yes?
We're just doing Wavepackets going in one direction, so it should be.
That's right. You see, here, this wave packet is going to be going in the positive x direction, as long as k is positive. It's just the direction is determined by the relative sign between those quantities. E is positive, and if k is positive, this moves to the right. As long, if I start putting things where k is negative, I'm going to start producing things that move to the left and to the right, and a terrible confusion. So yes, it should go 0 to infinity, 0 to infinity. And f of k, what is it? Well, in our usual picture, k, f of k, is some function that is peaked around some k naught. And this whole thing is psi of x and t, the full solution of a wave packet. So now you see how the A, B, and C coefficients enter into the construction of a wave packet. I look back at the textbook in which I learned quantum mechanics, and it's a book by Schiff. It's a very good book. It's an old book. I think it was probably written in the 60s. And it goes through some discussion of wave packets and then presents a jewel, says with a supercomputer, we've been able to evaluate numerically these things, something you can do now with 3 seconds in your laptop. And it was the only way to do this. So you produce an f of k, you fix the energy and send in a wave packet and see what happens. You can do numerical experiments with wave packets and see how the packet gets distorted at the obstacle and how it eventually bounces back or reflects. So it's very, very nice. So there is our solution. Now we're going to say a few things about it. I want to split it a little bit. So let's go here. So how do we split it? I say, the solution is this whole thing. So let's call the incident wave that is going to be defined for x less than 0 and t. This is for x less than 0, and the incident wave packet is dk 0 to infinity f of k e to the I kx e to the minus I et over h bar. And this is just defined for x less than 0, and that's so important that I write it here. For x less than 0, you have an incident wave packet. And then you also have a reflected wave packet, x less than 0. T is the second part, dk f of k, k minus k bar over k plus k bar e to the minus I kx e to the minus I et over h bar. It's also for x less than 0. And we have a transmitted, psi transmitted, for x greater than 0 and t. And that would be 0 to infinity dk f of k 2k over k plus k bar e to the ik bar x e to the minus I et over h bar. Okay, lots of writing, but that's important. And notice, given our definitions, the total psi of x and t is equal to psi incident plus psi reflected for x less than 0, and the total wave function of x and t is equal to psi transmitted for x greater than 0. Lots of equations. I'll give you a second to copy them, if you're copying them. So now comes, if we really want to understand this, we have to push it a little further. And perhaps in exercises, we will do some numerics to play with this thing as well. So I want to do stationary phase approximation here. Otherwise, we don't see what these packets, how they're moving. So you have some practice already with this. You're supposed to have a phase whose derivative is 0, and it's varying very slowly at that place where there could be a contribution. Now, every integral has the f of k. So that still dominates everything. Of course, you see, if f of k is very narrow, you pretty much could evaluate these functions at the value of k naught. And get a rather accurate interpretation of the answer. The main difficulty would be to do the leftover part of the integral. But again, here we can identify phases. We're going to take f of k to be localized and to be real. So there's no phase associated with it. And there's no phases associated with these quantities either, so the phases are up there. So let's take, for example, psi incident. What is the stationary phase condition? Would be that the derivative with respect to k that you're integrating of the phase, kx minus et over h bar, must be evaluated at k naught and must be equal to 0. So that's our stationary phase approximation for the top integral. Now remember that E is equal to h squared k squared over 2m. So what does this give you? That the peak of the pulse of the wave packet is localized at the place where the following condition holds, x minus dE dk with an h bar will give you an h k t over m evaluated at k naught equals 0. So this will be x equals h bar k naught over m t. That's where the incident wave is propagating. Now, look at that incident wave. What does it do for negative time? As time is infinite and negative, x is negative and it's far away. Yes, the packet is very much to the left of the barrier at time equal minus infinity. And that's consistent because psi incident is only defined for x less than 0. It's only defined there. So as long as t is negative, yes, the center of the packet is moving in. If I'll maybe draw it here. The center of the packet is moving in from minus infinity into the wall, and that is the picture. The packet is here and it's moving like that, and that's T negative. There's psi incident. It's coming from the left into the barrier, and that's all okay. But then, what happens with psi incident as T is positive? As T is positive psi incident, well, it's just another integral. You might do it and see what you get. But we can see what we will get, roughly. When T is positive, the answer would be you get something if you have positive x. But psi incident is only for negative x. So for negative x, you cannot satisfy the stationarity condition. And therefore, for negative x and positive time, T positive, psi incident is nothing. It's a little wiggle. There's probably something, a little bit, look at it with Mathematica. There will be something, but for positive t, since you only look at negative x, you don't satisfy stationarity, so you're not going to get much. So that's interesting. Somehow, automatically, psi incident just exists for negative time. For time near zero is very interesting, because somehow stationary phase condition says you still get something, but you're going to see what the packet does as it hits the thing. Okay, let's do the second one of psi reflected. ddk, this time would be kx with a different sign, minus kx minus et over h bar at k naught equals 0. For the reflected wave, the phase is really the same. Yeah, this factor is a little more complicated, but it doesn't have any phase in it. It's real, so ignore it. So I just change a sign. So this time, I'm going to get a change of sign. X is equal minus h bar k naught over m t. And this says that for t positive, you get things. And in fact, as t is positive, you are at x negative. And remember, psi reflected is only defined for x negative. So you can satisfy stationary, and you're going to get something. So for t positive, you're going to get, as t increases, a thing that goes more and more to the left, as you would expect. So you will get a psi reflected going to the left. I will leave for you to do the psi transmitted. It's a little different because you have now k bar, and you'll have to take the derivative of k bar with respect to k. It's going to be a little more interesting example. But the answer is that this one moves as x equals h bar k bar over mt. K bar is really the momentum on the right. And since psi transmitted exists only for positive x, this can be satisfied, this relation or concept can be satisfied for positive t. For positive t, there will be a transmitted psi transmitted. The psi transmitted certainly exists for negative t, but for negative t, stationarity would want x to be negative, but that's not defined. So for negative t, on the right, yes, psi transmitted Maybe it's a little bit of something, especially for times that are not too negative. But the picture is that stationary phase tells you that these packets, psi incident, pretty much exists just for negative t, and psi reflected and psi transmitted exists for positive t. And these are consequences of the fact that psi incident and psi reflected exist for negative x, the other exists for positive x, and that coupled with stationarity produces the physical picture that you expect intuitively, that the incident wave is just something, part of the solution that exists just at the beginning, then somehow it whistles away, some of it becomes transmitted, some of it becomes reflected.